Yes. Let me just mention a little bit first about GENIVI. Most of you probably haven't heard about that before. GENIVI, where IVI stands for in-vehicle infotainment, which is essentially just about all the interaction with dashboard and radio, navigation, whatever in the car. And GEN probably stands for generic. It's an alliance with including a lot of major players in the auto industry to try to create an open source platform for IVI and making that a standard. And this has been growing for some years, and there are already actually a number of models around the world that have that are being sold that at least use parts of these reference components. And well, you all know what the situation is basically with, you know, the car and your cars and electronics. You have usually you will use your iPhone or tablet and Google Maps rather than the onboard navigation system. Actually, I would say that, or studies show that several of the features that are actually sort of built into the car in terms of infotainment are not being used by almost half of the people using. I mean, there are a number of features that almost never get used. And part of this is because all the manufacturers so far have basically had to try to build this themselves from scratch, and it's an extremely complicated system of systems. And lead times are too long, and it's very difficult to understand or to foresee what is actually going to work when these cars hit the market. And the realization, this has led to the realization that they have to do this together, and it's not about competing with the iPhones and Androids. It's rather trying to create an environment where the consumer electronics actually can be integrated or cooperate with the car electronics in a way that feels natural and safe and productive for the users. And exactly how that's going to work, well, I think that it's one of the more interesting problems right now in the industry. And they also pretty much estimate that about 85% of what needs to go into an IVI system is generic. And the remaining is where each brand can try to distinguish itself and compete. So just looking a little bit at the members in the alliance, some of these logos are very small, but you have players like car manufacturers like BMW, Daimler, Hyundai, Volvo, waving the Swedish flag there, and some French, and most of the major Chinese car manufacturers, actually. You have a bunch of first-tier suppliers to the auto industry, and then you have other big players, like middleware players, down in the corner there. You see Ericsson, and they are also represented here today. And like I said, this is a very complex project, and I should also mention that the Linux Foundation is also part of this, a major player in GENIVI, and basically what they call AGL, automotive grade Linux. So part of this push is to do just about all of this. It's open source, and use Linux in the cars, use reference hardware, and create reference components for all these things. Also allowing, obviously, different vendors to then add their proprietary code. So what I'm going to talk about here is RVI, which is one part of the networking area, remote vehicle interaction. So the idea is to, the big things that we're trying to sort of support is obviously control, being able to invoke services, operate on the vehicle or whatever, and also pushing data to the cloud, big data, analytics, whatever, and SODA, which is software over the air, that is software update. And the main thing I'm working on is the transport component there. And in order to support these requirements, what we're trying to build is, or what we have built, is a peer-to-peer sort of multi or transport agnostic, more or less, or multi-transport system that supports service discovery, authentication, and authorization. So basically, we can take the next picture here. That, say you could have services in the cloud, services in the mobile device, that is the car, or this is pretty generic. So if you're not interested in cars, you can think other areas where you would have similar use cases. And you could have on your mobile device, one of the demos we're working on is door lock, unlock, extremely useful. Actually, it's kind of cool. It's especially cool in the demos when we have very nice cars. Everyone wants to be the person who gets to unlock the sports car and drive away. So we have different types of transports, and in order for this to work, we also have to support not having internet connection at all. So in some cases, you might be able to reach the car with an SMS, so that you can possibly rely on GSM working at least. In other cases, you may have your mobile phone and a Bluetooth connection. And we're also, in some cases, there may not even be a connection at all, that you basically just have to do manual interaction. But that is a slightly different case. So for security, we are relying on OpenSSL, X509 certificates. And on top of that, we also use something we call credentials, which is our own little data structure that explains what kind of services I can invoke, I am allowed to invoke, and what kind of service invocations I am allowed to receive. So, for example, in the unlock case, first you'd connect over an SSL connection, typically, and you would exchange credentials, and then you would try to send an unlock command, and the vehicle transport component will verify that you are actually authorized to issue, for example, an unlock command. And once you get that far, it will trigger whatever interaction is required. So in the demo, you would typically have a Raspberry Pi that fakes pressing a key fob, and the car is unlocked. So in order for this to work robustly, the system needs to be able to choose between different transports, and also needs to be smart enough to not, for example, send a software image over a roaming GPRS network or something. So you need to be able to put in conditions so that it can be rate aware and things like that. And you can also do some basic routing so that you can either go point to point or go via some service that can then forward the request. So I'll go through a couple of scenarios that we're working with. One is software over the air upgrade. Now, part of this obviously is standardizing the whole procedure and the components in the car and everything so that this can be done in a generic way. But here you would have typically a server in the cloud that keeps track of the different software components and the different versions. And then you would have a SODA client in the vehicle that understands how to implement the actual upgrade inside the car. And the workflow would typically be that you queue the software update. Obviously, you have to be sensitive to when this is actually done. It's preferable to do it when the car is not driving down the highway, for example. So you transmit the software to the vehicle. Obviously, these are large software images, so that that would actually impose some new restrictions. You probably don't want to send a couple of megabytes and have it fail halfway through and things like that. We'll get back to that. So another demo that we have is the mobile unlock, as I said. Now this would be very generically, use any smartphone to unlock any vehicle, well, provided you are actually authorized to unlock that particular vehicle. A use case could be that someone wants to borrow your car over the weekend, or there are some services where you can actually register your car for peer-to-peer car rental, where you would want to authorize somebody to actually open your car and drive it for a while. So then what you would want to do is you want to send them a virtual key that they can store on their smartphone, so then when they get to the car detects that they're there, authorizes them, and lets them in. So what we have then is a key management website, a demo again, which provides a credential signed by using a root certificate that is also installed in the car, so that it can be validated when the devices connect, that this credential is actually signed by an authority. And this is where we use the root certificate to verify that. So we have this implemented on Android and iPhone. And the demo software in the car runs on a Raspberry Pi and using just a simple key fob. So we somehow manage to transport the credential to the mobile phone, which stores it in the app, which can be surprisingly difficult on iOS, but it's doable. When the phone approaches the vehicle, either you use Bluetooth, and the car can detect when you're in range. We've also had some, Christopher Granovsky over there can talk to you later about how fun it is to hack the Bluetooth stack to make sure that it can sends your approach vector to see that you're within a good range of the car, not necessarily 40 yards away, but actually being fairly close to the car and approaching it, and then you actually connect over Bluetooth. And then when you connect, there is a handshake, credentials are transmitted, and then after that, you can send the unlock command. Another use case would be, for example, to deploy a probe in the car. Owners of a certain make, for example, have reported problems, perhaps intermittent problems or whatever, as they're driving, and then you would prefer not to just recall all cars or just hope that you will be able to detect this scenario. Maybe it only manifests when you're driving on the highway, and only sometimes, so you're not likely to detect this in the auto shop. So then what you can do is you can deploy a probe that starts collecting data and passes it up to the cloud. And this could be also some third-party entrepreneur, perhaps working with car sharing, whatever, and they want to track the usage of their cars. They buy what we call a V2X board. Here's a V2X board, that one. That's a normal Raspberry Pi. And V2X stands for vehicle to vehicle or vehicle to infrastructure, for example. And they implement their service on that. And the purpose of that board is that if you can make it work on that, then you can talk to a car manufacturer later, and the same, that architecture should be compatible with what's in the car. So then that way you can install your own stuff and run your own demos or prototypes or your own services, and then there is a standardization path. So the V2X board looks like this currently. It has an accelerometer, a modem, and those are antenna sockets. So currently we get the GPS, we can get the GPS signal from there. You also have a power management unit, so you're going to be able to send, for example, a wake-up SMS, so that this can power up the Raspberry Pi. There is a CAN bus interface. So it's a reasonably nice board. The version 2 will actually combine these two into one board. And the design is open source. So if you want to manufacture it yourself, you can go ahead and do that. But there are places where it can be purchased. So health monitors, where, for example, you would, if you're an OEM, you would use the reference implementations that sort of built into the car. If you're an entrepreneur, you would use the V2X board. And as I said, these are compatible. Other things would be, for example, tracking feature usage. Or tracking Bluetooth problems, for example. That's actually a very common problem reported by car owners, that the Bluetooth is not working as it should. So those would be some use cases. I mean, these are basically the demo use cases that we're working with now. But the whole idea is to provide an open and eventually standardized interface, and that actually is usable for entrepreneurs, third-party providers, service providers in the cloud, people who want to actually install stuff in the vehicles or wherever. So just looking at the RVI transport, this is implemented in Erlang, which is a reason why I'm actually standing here and talking about it. The architecture is, you have various components. This is the service edge, is where various applications would talk to the transport or the RVI core. And this would usually be, currently it's either JSON RPC or over HTTP or WebSocket. Now the service edge will talk to the authorization component, which verifies the credentials. This schedule component here is actually a form of a router and store and forward. You have a service discovery, which shares service announcements with connected nodes. And then you have the different data link layers. And I would say all the features implemented in the Erlang implementation are usually not available in the cell phone SDK. But also, typically, what you would want to do from your cell phone is just connect to a vehicle or to a service and get authenticated and then invoke some services. Now, the handshake protocol, first a standard TLS upgrade. We mostly use self-signed certificates and have the root certificate installed on the RVI core node. So once we have validated that, now if you use TLS. We also have a TCP transport where we just skip this. And that would be mainly for development, because obviously it is no longer secure, but it allows you to implement and test the rest of the stuff. Then you send an authorized message, which includes the credentials encoded as JSON web tokens and signed using the root certificate's private key. So they can be validated using the root certificate public key, which the RVI node has. So once you have that, you can look at the credentials and figure out which services to announce to the other side. Basically, the services they are allowed to invoke are the ones that you're going to tell them about. So then you send service announce messages, and on the other side, the receiving node will look at those services. It will check authorization against the credentials that it has and cache them so that it can quickly approve service invocations afterwards. It sends, now these authorized commands go both ways. Also, the service announce messages go both ways. So it's peer-to-peer. And after that, you can start invoking services. And that's called I think a receive command, I think it's called, or message. Don't remember. So the credential will look like this. You will have some timestamp, validity timestamps, some IDs and issuing organization, but these are the things that control the what you're allowed to do. The right to invoke, these are patterns matching various services. And usually they will look like manufacturer, and then some vehicle identification number, for example, and possibly a path beyond that. So each node will have a sort of a service prefix. So when you register services, say I register an unlock service, that will be appended to that node's service prefix, and that's the full name that you would use in order to invoke that service. Right to receive is which service invocations I am authorized to receive. So then it's up to the other node to make sure that it doesn't allow service invocations going to me if I am not authorized to get them. Now, for large packages and reliable delivery, this is all asynchronous. The service invocations are send and pray, basically. So, but if you want reliable delivery, you can use the fragmentation support. And that basically works like this. You first send a first fragment. Now, that could possibly be the whole message, depending on how you've configured it. You can configure it using a max message size, but you can also turn it on by just saying, I want reliable delivery. And then it will send the whole package as a fragment, saying this is the message ID, this is the size of the message, and here's the offset of this fragment. The receiving side will take that, and it will try to reassemble it and check whether it has the entire message. If it has the entire message, it will just send a fragment end, which is the acknowledgement. Otherwise, it will request the next fragment. And then it will provide an ID and the offset and how many bytes it wants. And then you will send more fragments. So in the reassembly, you basically identify holes in the package if there are fragments that have gone missing, and then you can request them again. What would be nice to have that I haven't implemented yet is timers, which is obviously a pretty serious defect, but so the Service Edge API, you can register services, unregister services. You can ask what services are available, and you can send a message, which is basically the service invocation where you name the service. You can provide a timeout and parameters. And these are more the internal API, service available, service unavailable, handle remote message. That's a message that comes in from another node, or handle timeout. I have planned to implement message pack RPC on the Service Edge, since it's a lot less overhead than JSON RPC. We are using message pack encoding between nodes, or JSON if you want. But especially sending large packets over JSON is pretty painful. In terms of routing, right now we have pretty simple routing logic, but you configure that basically, again, matching on the service prefix, and then you have protocol modules, various options, and this is basically you will try from the top going down, and for each matching transport option here, you will try to see if they're available, and you will just go down the list, and usually you will have a catch-all down here. But if there are no matching transports or sessions, then you buffer the message, and then you will try again if transport becomes available, Right now we're also implementing netlink subscriptions so that we can detect when an interface comes up, and so that we don't have to sit there and retry or poll periodically to try to see if we can get out. And what we're going to do is we're going to expand this so that you can also sort of configure and match on rates, for example. We'll see exactly what will be useful. So that is basically it. The status is we are recently released version 050. It's on GitHub. It's using an MPL license, MPL 2.0, which we think is a fairly good license for those of you who are not aware. It's kind of like the Apache license, but it does force you to publish your contributions. So you are allowed to do whatever you want with it, but you need to make your. It's kind of like the Erlang public license used to be. So we believe this is usable for pilots, and we're going to start running more serious pilots pretty soon, and are developing our demos. We do build Debian packages, and the recommendation, by the way, is to use the Erlang Solutions packages for OTP 18.2 or later. We also build Raspbian packages. Unfortunately, ESL hasn't updated their Raspbian package in a very long time, so I think, but we do have some build instructions. It is quite doable, but you have to be. It would certainly be better to have a Raspbian OTP package. There is an automated test suite using Common Test, which test suites can always be improved upon. There is an Android SDK and an iOS SDK. There are some Python support libs for registering services and invoking services, and they are at least sort of a starting point to play with. We are also building some demos using Lua. So the idea is basically to be very open about from which clients and which languages you can use this. So the fact that the core protocol is implemented in Erlang is not something that people will have to worry about. And I guess you could, now some Ericsson people might cringe here, but actually the way it is implemented is that all these components are at least theoretically possible to break out so that they can run separately. And so these APIs have sort of a JSON RPC implementation, and hopefully soon a message pack RPC implementation, because you get quite a big performance hit when you go from using a Gen server to using JSON RPC to communicate. But on the other hand, it would allow you to distribute and get better scalability that way. But it would also allow you to break out certain components and implement your own logic. And that's actually a sort of an environment variable configuration part where you tell it whether it's just the internal implementation or whether it's using JSON RPC, and then you just provide an address for it. and all the everything should work the same. I will say that this is not something that we have actually tested in the latest release. It did work in a previous release, and if it doesn't work anymore, it's probably just because we've accidentally broken something. So it's 0.50, we're not at 1.0 yet, so there are a couple of things like that if any of you would like to try that out, I'd be happy to have you send bug reports. I could say that, what could I say? Yes?
So I guess first, are there any hardware manufacturers making components that will talk to RVI Protocol currently? And what is port sockets? Are you going to be running Ethernet through the car to connect these components? Or what's the idea there? Control HVAC, radio?
Yeah, that didn't work. So I'll just. So most of the communication in vehicles is through CAN buses, and whether it's going to be Ethernet in the car, I'm not sure. So sort of at the phase where I'm working, that's not really something I get involved with. And in terms of the RVI transport, it doesn't really matter.
Well, that service engine needs to know. You mentioned WebSockets.
Yeah.
Or HTTP. Can you do WebSockets over the CAN bus?
No. That's the RVI communication is not going to go over the CAN bus, but whether it's wireless or it's probably going to be something like Ethernet or whatever. But that would be up to each manufacturer. As far as usually for the RVI core stuff, what would happen is that this transport is mostly for outside services or devices communicating with the vehicle. And then the service that is registered to RVI core and gets invoked right now through JSON RPC, it is responsible for actually interacting with whatever it is. So in the unlock demo, for example, that is just a Raspberry Pi board where the GPIO pins are connected to a key fob, and it will just manipulate the key fob and unlock the door. So, and in that sense, it's just RF from the key fob. So it depends on what kind of, and if you're using the V2X board, you would connect to one of the CAN buses, depending on and which one depends on what it is that you want to do. And I could say that we are, for example, implementing, trying to specify a messaging. One thing we're implementing is a CAN firewall, because if we're going to invite a bunch of third-party services to communicate on the CAN bus, we would like to be able to control what they actually do. So we have a reasonably well-working CAN bus firewall. We're also specifying a message passing interface for if you want to pull tons of data, and it can really be an enormous amount of data from the vehicle. We've found that most of the third-party or the existing messaging solutions are simply too slow. We will use dbus, for example, for the administrative or the control signaling, usually in the car, but dbus is too slow if you want to pull tons of performance data from the car. So we have something right now we have some prototypes where currently when we are able to do sort of a publish to 30 threads listening in parallel at a rate of about 8 million signals per second, which we think is reasonably good. And I think with just one thread, it's like 18 million. And I don't know exactly what RVI core is going to do when those messages, you're going to have to filter and aggregate before you push it out over the internet, obviously. I was going to show you, but for some reason the screen didn't want to talk to my Ubuntu VM. But in terms of performance, I can say that in my test suite, I, for example, have one test case where I fire 5 service invocations in parallel that go through 2 RVI nodes and loop back to a JSON RPC server running in the common test environment. And that usually completes in a couple of hundredths of a second, something, or 30 milliseconds or something. I don't remember exactly the.
Is the CAN bus on your development board, is that over serial to talk to the CAN bus on the Raspberry Pi?
Yeah. So what we've seen so far in our demos is that, for example, if we are controlling the HVAC, actually my clock was reset, so I lost track of the time.
You got 6 minutes.
Yeah. So what we've tried to do there is that if you, for example, want to update the air conditioning, or you want to control the FM radio from your phone, what we would like to do is to have this be fast enough that you can actually sort of individually update widgets on your display without feeling that there's a noticeable delay. So it's not supposed to appear slow. And so far, that seems to actually work. And we've done some optimizations since then. So at least it seems fast enough that you can have a pretty good interaction with the car, for example, over Bluetooth from your phone to, or Wi-Fi from your phone to whatever you want to control on your dashboard. So I think it would be fun to discuss other possible uses of this. We discussed, for example, home automation. I'm staying at an Airbnb apartment. I can imagine a couple of use cases there where you get authorized. Right now, you get a PIN code to the door, so that you can just unlock the outer door. But that's kind of it. And then happily, they have provided a Wi-Fi password. But I mean, there are obviously a lot of things that could be implemented using this kind of service invocation and authentication or authorization framework. Any other questions? And I'm sorry I forgot to repeat the questions, but they were spoken so loudly that, yeah.
Thank you.
Okay, thank you.